let's begin. So for today's lecture, we're going to continue our discussion, which we left off last week. And we'll talk more about design pattern. Today's lecture is going to be relatively short because there is just about a bit more than an hour content left for this topic. And then we're pretty much on track on finishing all the contents for this course. So since we have some extra time, I first want to talk about our the remaining part for this course. So just take a look at this academic calendar. We have about 2 more weeks for this course. So that means we have 4 more lectures, including today. So today we're going to finish our discussion on design pattern. On Thursday, we will talk about DevOps. And that's pretty much all the contents that's offered from the Berkeley course. And then for next week, the first day, the Tuesday lecture next week, we will watch some bonus content for project management, and then especially looking at this procedure from the developer perspective, and then for each PM stages, what's our role, and what are the typical activities we do, and then some good practices when involved in project management procedure. And then for the last lecture, we will have go through a recap and just review everything we've talked about in this course, and kind of reflect on every single practice and what are the trade-offs, what are the benefits from each practice, and then what we lose by following certain practice. And that will be the remaining 4 courses. Then we will have our final, and I've decided not to do final exam, simply because everybody is located in different time zone, which makes the final exam extremely tricky, especially when I think about timing. So, still there are 2 options for the hands-on or the bonus option. You could still finish a project of your choice, just either your side project or a project you're working on, or just any project, a programming project, and then apply what you've learned, primarily, stuff like testing, dealing with legacy code if the project involves legacy code, behavior-driven design, iteration, that kind of thing. And then also even, if you get a chance, even the stuff we're going to talk about this week, and then something we already talked about, like design pattern, like DevOps. So the bonus option for final project is stay the same, but for the basic option, instead of having a final exam, I'll just ask people who choose that option to write an essay on what you've learned in this course. And then the subject of the essay could be as simple as a summary of the entire course, or if you're specifically interested in certain topic, like for example behavior-driven design, or BDD, or maybe you're interested in just Agile, the actual workflow. You can pick one of those focused topic as well for essay, and then do some research, read some paper. You should be able to find enough paper on places like Google Scholar. For example, let me just show quickly. Google Scholar. For example, if I want to write an essay about behavior-driven design, let me actually enlarge it. So this is Google Scholar, behavior-driven design. You should be able to find enough papers on that topic. Most likely, you would want to find papers that are cited most. For example, this one over here, which is cited by over 600 other papers, and then cited by 100 times. That's not bad. That's not bad either. 200 times. Like, just find a couple of these papers if you want to, write about a certain topic that we've discussed in this course, and then you read through the paper, summarize what you've read about it, how it connects to what you've learned. Or you could just write an essay, not just talking about the summary of what you've learned. You could also give your reflection, given your previous experiences, whatever stuff that's related to the topics we've covered in this course. So that's also an option. And then I'm still thinking about how many words will be required, but probably it's going to be around like a 5-page Word document or something like that. Might be okay to have shorter, so I'm still thinking about that. But for if you choose to do the essay for final, that's also, I just want to put it out there. And then there will be no final exam just because of the time zone issue. Okay, so hopefully that's clear. And that will be our timeline. So this week we'll finish the Berkeley course. Next week there's some bonus content on project management, and then we will have a review of the entire course. And the week after next one, it will be the final period. You can work on your final project, finalizing it. And then if you choose to do that, a presentation will be required, so I'll ask you to schedule a final presentation with me if you go with that option. Otherwise, you can take the week to write your final essay. Okay, so that's about our remaining schedule and a bit about what I'm looking for final. Okay, so now then, let me also actually talk about this week's homework before we begin our content. So for this week, the basic option will be write the summary of the last chapter from the textbook, and then the chapter will be talking about DevOps. So we won't talk about DevOps yet today, but we'll talk about on Thursday. So if you go with the basic option, I'll ask you to write a summary about that chapter. And then if you want to go with the bonus option or the hands-on homework, you just need to continue your work for last week, which is the Agile iteration project. yeah, so nothing changed there. There's no additional hands-on homework for you if you choose to go with the bonus option. All right, so that's all the stuff that we need to talk about for the course. Then as of today's lecture, we will continue to watch the remaining video we have left off, and then learn more about design pattern.
The first of which is Liskov Substitution, so called because Barbara Liskov, who won the Turing Award in 2008 for her work on abstract types, is generally credited with the formulation of what we now sort of take for granted as inheritance in object-oriented languages. And basically, her formulation is, if you have a method or a function that expects an object of type T, then if that object has subclasses or subtypes, it should be legal and correct to pass any subtype of T to the function, and it should work just the same. And I think I was, when she actually won the Turing Award, she gave a lecture at a conference I happened to be attending. And I remember there were some students sitting behind me, and they put something like this up on the screen as a, here's what Barbara Liskov is winning the Turing Award for. And somebody behind me said, why would someone get an award for that? Everybody knows that's true. Anyway, this really happened. OK, so technically speaking, the way that she was using the term type and subtype in terms of formal language semantics is not identical to the way we would use class and subclass. But for our purposes, it's pretty close. And since we know that in Ruby, there's no typing rules in the way that a strongly typed language like Java has them, right? It's not illegal to pass objects of the wrong kind around as long as the interface that they export is correct. Nonetheless, the idea of substitutability still applies and is still an important idea. So again, I'm going to show the examples in code right on the screen, but if you want to look through the examples offline, I put them up as GitHub gists, and you can follow the links on your own anytime. So here's sort of the canonical example of what can go wrong with Liskov substitution. I'm simplistically assuming that I've defined a rectangle class. Rectangles have a width and a height, and a location on the screen, which arbitrarily we're saying is the top left corner. You can create a new instance of it. You can ask for its area and perimeter. Or you can have this, here's a special function that will take a rectangle and make it tall and skinny. So while preserving the area, it'll make it just twice as wide and or twice as tall, half as wide. And if you now say, well, I also need a square, but really a square is just a kind of rectangle, because in some sense, every square is a rectangle, although not conversely. So a square, if we say it's a subclass of rectangle, we run into the problem that when we try to set its height or width, the whole problem with a square is that those are supposed to be the same. The real problem is that if you try to pass a square to a function that expects a rectangle, and that function tries to call make tall and skinny, which is a perfectly legal thing to do on an instance of rectangle, then square is in trouble, because there's no way that it can realistically implement that, right? So of course, in this contrived example, the real problem is squares maybe aren't really a subclass of rectangle. We should have thought that out better. And we'll fix that in a moment. But the idea is to illustrate what can go wrong in that situation. Because even in a strongly typed language, if we had declared square as a true subclass of rectangle, then from a type safety point of view, the compiler is concerned, it's perfectly legal to pass a square wherever a rectangle is expected. And yet, it is possible for the thing that you pass to be asked to do this behavior, which is totally incompatible with squares. So the sort of hacky workaround that you sometimes see for this is square as a subclass of rectangle will override this method, and it will do something like raise an exception saying, sorry, I'm a square, I can't do that. But that's kind of a bad deal, because the whole point of a subclass is you do everything your parent class does, but maybe you also do some other things, or you specialize or override some of those behaviors. Right? So this is why this example is said to violate Liskov substitution. Even though square is declared as being a subclass of rectangle, it is not the case that it's always OK to use a square anywhere that you use a rectangle. So how to fix? We'll show the class diagram version first, and then we'll go ahead and show it in code, which everybody understands and is warm and fuzzy. But again, one of the common elements, and this came up when we did the open-close principle and single responsibility, is there are many ways to misuse inheritance, and a lot of them can be addressed if instead you do composition. So remember what composition means. It means that we've got an object, one of whose components is an object of some other class. And between those two, between the containing object and the contained object, there can be some delegation of work. So basically, the insight here is there are many ways in which a square is like a rectangle. So what we could do is, rather than having what's on the left, this is what was on our previous slide, where we're saying square inherits from rectangle. That's not the only way that a square can reuse the behaviors or the work already happening in rectangle. Another way it could do that is what's on the right. Square is now a separate class. It does not have an inheritance relationship to rectangle, but we give square as one of its components an instance of rectangle. Because then, if you ask the square for things like its area or perimeter, it can delegate those calls to be done by the work in the rectangle class. It's no longer a subclass of rectangle, but it basically has inside of it an instance of a rectangle to which it can delegate that work. And what does that look like code-wise? Here's the simple version. Here's class square, which, as you see, no longer has any direct connection to the rectangle class. But when we create a new square, and all we have to specify is the length of a side, we will create a rectangle instance inside of square that has the correct dimensions. So that when you now ask the square for its area or its perimeter, all we're doing is passing those calls on. We are delegating the calls to the instance of rectangle. Now, square is no longer obligated to do something sensible when you say make tall and skinny, because it's not a subclass of rectangle. It is no longer assumed that you can pass a square anywhere that a rectangle is expected. You can still use a square in most places a rectangle would be expected, because maybe what you were really after is the idea of a polygon that has standard ways of computing its area and perimeter and has 4 sides. So you do want to selectively reuse some of those behaviors. And if square and rectangle implement some of the same methods, because Ruby has this nice duck typing concept, they probably are somewhat interchangeable. But you're no longer asserting that they have to be substitutable one for the other in the Liskov sense. It happens to be the case that if you're using Rails, which includes this active support module with a bunch of goodies in it, you can actually just say delegate area and perimeter to some attribute named by this symbol. So basically this says if area or perimeter is called on an instance of square, look for a component of square whose name is rect, and there it is, and assume that that is an object that will be able to handle the calls. So it's a shortcut for delegation. But all it's doing is exactly what I've done here explicitly, which is I receive the call, and I have somebody else do the work. Okay, so what's the sort of meta pattern here? It's that we've replaced an example of using inheritance as a way to reuse work with instead the combination of composition, right? So we have inside of a square, we have an attribute that is an instance of a different class. Composition plus delegation. We use that contained object as a way of delegating some work so that we don't have to re-implement that in square. So we're sort of trying to get some of the benefits of reusing behaviors that you would get from true inheritance, but without having to pay the price of true substitutability. A square is not enough like a rectangle to make that work. And by the way, symptoms. One symptom is what's called a refused bequest. Why is it called that? Because when you have a subclass, it is said to inherit all of the behaviors of its superclass. But in our example, square was not able to inherit the behavior of making itself tall and skinny. So you'd have to do something to override that method in square and raise an exception saying, I know I'm supposed to inherit that behavior, but I can't do that behavior. So it's called a refused bequest. The other symptom is what's called shotgun surgery, where the way that you fix the problem is, well, the real problem here is that rectangle should never have had this method. So I'll remove this method from rectangle, and then it's OK to just make square a subclass. You can do that, but now you got to look for every place that used a rectangle and figure out if removing this method is going to have an effect in any of those places. So because you're sort of looking all around in your code and trying to find all the places you might have caused some damage, that's called shotgun surgery. So that is another symptom, if you find yourself doing that, that maybe the problem is it wasn't really an inheritance relationship to begin with. So to summarize, what does Liskov substitution say? It basically says if you're inheriting, you bought the whole farm. You have to agree that every behavior that your superclass does is something sensible that you can do. Otherwise, it's not really true substitution. If you find in your code that you are having to come up with examples where you have to go out of your way to say, no, I can't do that for an inherited behavior, that's a likely sign that you are doing a Liskov violation. And how do you fix it? Many times, the reason that the problem arises is that inheritance was not the right mechanism to begin with, that there is a better way to reuse the behaviors you want, and a very common way to do that is composition. You take the object whose behaviors you want to reuse, you make it a component of some other object, and then you selectively delegate some calls on the containing object to be done by the work of the contained object. And that's what we did in our example. We just explicitly receive the call and just forward the call onto someone else. Okay, so composition plus delegation is generally the pattern.
All right, so here we see the argument again, composition over inheritance. And I think we will see it one more time. But anyway, the idea is, and then also according to my experience so far, it's almost always better to go with composition rather than inheritance if you have the choice. Sometimes you don't have the choice. For example, if you're writing a Rails application and then you're defining a controller or a model, then probably the only document, although there will be other documentation, that will be hard to find. But probably the most documentation you would be find is just straight up inherit from the active controller or action controller, and then from the active record for a model. And then in those cases that actually makes sense because the parent model or the parent class already have many stuff packed into it, and then it's very, very unlikely you will need to modify it. But then, for example, if you have a model, for example, a user model, and then it actually makes sense to inherit from active record and then use composition pattern. For example, the popular stuff you would use like device for authentication, OmniAuth for single sign-on functionality, that kind of thing. Those are composition. You basically extend the user model with the other modules or functionality that comes from other gems. So here you can see, actually the Rails community is still very much pro composition rather than inheritance, because imagine if like a gem forces you to inherit from whatever their class offers. Let's say for device, if you have to have your user class inherit from another class that they defines, and that class inherits from like active record, then it's gonna be a little messy to manage. And then let's say you have two type of user model that all supports authentication, then it'll be very difficult to program that. But with composition, because you're basically extending the existing class with the additional module of the functionality, so it works pretty out of box. And then probably you can see more examples there. But the idea is, unless there's a really good reason to do inheritance, or unless you really know that the child class will never modify the existing methods or function that's defined in the parent class. So unless you're really sure those won't appear, you're better off just go with composition. But if you can be sure, you know that this class, the subclasses will always have the same interface that's inherited from the parent class. Maybe they can have some additional interfaces, but not like deleting one method or modifying one method, then inheritance might make sense. Yeah, so basically, unless you're really sure or unless you have a really good reason to do inheritance, otherwise composition is almost always the better option out there. Yeah, I think later we will see more examples in the remaining videos. So yeah, I would just end my comments here and then add some more to it later. All right, let's move on to the next video.
Let's move on to injecting dependencies. And this is a really good one, and for what it's worth, it seems to come up a lot in interviews. So my former students have said. So take that with a grain of salt. Sometimes you will hear this called dependency inversion, or as opposed to dependency injection, but they refer to the same thing. And as I said when we started talking about solid in the previous lecture, officially dependency injection is the D in solid, and the I stands for another principle that we won't talk about, which is interface segregation. But either way, whether it starts with I or D, whether it's injection of dependencies or dependency inversion, it's all the same thing. And the problem it's trying to solve is you have a scenario where you've got two components. One depends on the other in terms of the way that it expects to call it. But not only the implementation, but maybe even the interface of component B can change. So again, if we do it backwards from an example, suppose that I have something that I want to be able to use as a session storage like cookies or something like that. I have a database, and the functionality is clear. I want to be able to sometimes store a session in the database and maybe retrieve it later, so the way that, for example, cookies work in the frameworks that we've seen. But the problem here is, what if you decide that databases shouldn't be the only way to store sessions? Maybe you have a way to store them in something that doesn't look like a database. Maybe it's a cache, or maybe it's a file system. So the idea of storing and retrieving the session has not changed, but the kinds of calls have changed quite dramatically because the type of thing you're going to use for session storage may change out from under you. So the reason it's called dependency objection is that counterintuitively, the way you fix it is by creating a new dependency that doesn't already exist. And it ends up looking like this. You say, well, we're not going to ever have session stored directly called database. We're going to create this intermediary thing, which is really just an interface. All it does is provide a common, well-known set of calls to whoever the caller is above it, and it will translate those into whatever it looks like for the thing below it. Sometimes, but not always, the thing below it is implemented as true inheritance, but I'll show an example where that doesn't need to be the case. And there's a few different variations of this pattern, but basically all you're really doing is you're inserting a layer here that essentially hides not only the implementation, but even the interface of the thing under it. So now, if we replace database with file system, a file system is not going to have calls like read from database or store in database, but that's OK because Session Manager no longer cares about that. It just knows that the session store interface provides generic get session and store session or something like that, right? If the match between the underlying interface and the one that you're injecting is almost one-to-one, sometimes people call that an adapter or a facade. But the important concept is you are deliberately inserting this layer of indirection. And we all know that's how you solve problems in computer science, right? You insert a level of indirection somewhere. This level of indirection's job is to keep the interface stable looking up the stack. So Session Manager never has to worry about it. In terms of the way this is done in Ruby, very often this middle thing will be a module, because a module is a great place to put a namespace. But that's a secondary consideration. The architecture here of, instead of having session store depend on the interface of a database, we create a new generic interface that hides everything about the interface below it. That's actually the important bit. And you've actually seen a couple of examples of this in action, because Active Record sort of already does this. So I'm going to show you, let's see, which two examples do I have queued up. So the first example is Active Record itself. So if you look at the source code for how Active Record is organized as part of Ruby, think about the issues that it has to deal with. The whole point of Active Record is looking up, right, for the models that use Active Record or subclass from it. It wants to provide a consistent set of abstractions for what it means to talk to a database. But it turns out that even if you're looking only at relational databases like MySQL, Oracle, Postgres, SQLite, the specifics of how the interface is exposed to a client are quite different among those. Right? They all support the same kinds of operations, but the interface signatures are quite different. So if you look at the source code for Active Record, this is how it's actually organized. Active Record base has a method called connection. You never use that method directly, but all of the code in Active Record that talks to the database does use it. But that method is really just an interface to something called an abstract adapter. The abstract adapter provides a common set of database-y-like operations with a common set of names that Active Record base can rely on. So you can establish a connection, you can ask if the connection is free, you can try to send a query over the connection, various things like that, even though, depending on the specific type of database, the way those operations have to be done against that database are very different. So again, what's happened here is instead of having Active Record base essentially try to talk directly to one or another kind of database, right, which doesn't work because even the names of these methods are going to be very different across different databases, a dependency has been injected so that the only thing Active Record base relies on is what are the method calls available through abstract adapter. Abstract adapter's job is to map each one of those possible method calls to the right thing for some other database, which means each database has to have an adapter that is able to take its operations that it can provide and somehow make them look like something that abstract adapter can map to. Right? So by doing that, we have completely isolated not only the implementation of the database from Active Record, but even the interface to the database. Right? That's the problem that dependency injection solves. Sir?
Just drawing an analogy to like my own project this semester.
Yeah.
There's a proxy file there between models and the Oracle server. So is that similar to what's happening here?
What did you call it?
A proxy file. So
Proxy. I think we may actually be about to do there's actually a variation of this called the proxy pattern, and if you give me a few minutes to get to it, and if I have not by then answered your question, can you remind me and we'll come back to it? OK, coolio. So again, what are the mechanisms being used here? Delegation. This connection method in Active Record base doesn't actually do anything. It just forwards the call to the appropriate method in abstract adapter. Overriding, so the connection method in abstract adapter has to eventually look like something that each of the individual database adapters can do, and these are usually implemented by inheritance. They don't have to be, but they usually are. For what it's worth, if it turned out that inheritance wasn't a reasonable mechanism here, we could pull the same trick. We could say abstract adapter just has an instance of MySQL adapter as one of its components, and it will selectively delegate calls to it, maybe mixed in with some other code. Okay, but again, what's the key thing? This injected dependency, right? It got put between the two things that otherwise would have been dependent on each other. That's why it's an injected dependency. And it isolates, giving a stable interface looking at its caller and making sure that all of the callees can somehow be mapped into that interface. I'll give you another real-life example. And this one has to do with supporting external services. So I have an app in which I use external services for email marketing. If you've ever heard of MailChimp or Constant Contact, these are services that let you send large volumes of email to targeted groups of people. And for various reasons, you should never try to do that in your app. You should rely on a reliable external service to do this. So both of those services have nice RESTful APIs. They are designed to be integrated into other software as a service. And both of them generally do the same kinds of things. They let you have different lists of customers. They let you sort of schedule an email for sending, detect whether a particular customer has opted out, all of that other stuff. But the interfaces they present, right, their RESTful APIs for how you do those things are quite different from each other. So I had to pull the same trick. My customer model has, as one of its components, a thing called an email list. And the email list is actually kind of like the abstract adapter. The only thing it presents are the methods that its caller would ever care about. So from the point of view of maintaining a customer model and asking if that customer should be on the email list or not, the only thing this model cares about is opt in the customer, opt out the customer, and maybe update the customer's email address if they change their email address on the marketing service. So all these other services do a whole bunch of other stuff. But from my point of view in my app, my caller is never going to care about that other stuff. That's all it cares about. So the job here is provide a stable interface so that it's always safe to call these. And just like in the example above, I also have a class that wraps the actual RESTful API for MailChimp. It happens to have API calls that have names like subscribe, unsubscribe, update member. So in this case, the mapping is actually pretty close, but I don't have to worry about that anymore, right? I've isolated the specifics of this interface from the caller by injecting the abstract email list in between. And in the future, I have been asked by one of my customers, they don't use MailChimp, they use Constant Contact, which is a competing service. I actually don't know what the Constant Contact API is. I just know that they have one. And I'm sure that somehow, in terms of that API, I can get these things to happen. But once I figure this out, the customer model won't care, because all of its API calls are basically through this injected dependency. Right, so this is a really, really cool mechanism. In this case, some people call this the facade pattern, because in this example, even though the actual things that we're calling, that leaf of the tree, it has all of these other APIs for other things. But in our use case, the only set of things we cared about is this small set of stuff. So it's not just that it's sort of providing an adapter to mask the differences between the interfaces. It's actually providing a much simpler version because we only care about using a subset of stuff. So not that it's like the terminology is not super, super critical, but if you care and people say, oh, we had to create a facade adapter over something, what they usually mean is that the facade may take a subset of the underlying API, or it may unify distinct underlying APIs into a single one. So for example, if you read the documentation for the MailChimp REST API, these 6 things are actually 6 different RESTful APIs with 6 slightly different endpoints. But again, all we care about is, can we do these 3 things? From our point of view, this is a single set of related API calls, and that's all that the application ever sees. So that's dependency injection, and don't be surprised if this comes up on a interview-related question. I will get to the proxy pattern. I want to talk about other adapter-like patterns because somebody brought up an example of one, and I think it's probably going to be covered in this discussion. So in general, an adapter-like pattern is one that follows the general approach that we just saw, which is, for whatever reason, you have one interface, and you want to adapt it by putting some sort of a layer on top of it. Maybe it's because you want to shield the caller from changes. Maybe it's because you want to simplify the caller's view of that interface. So the dependency injection that we just saw using the adapter and the facade is one example of this. Here's a couple of others that come up pretty often. My favorite of the others is probably the null object pattern. And the idea behind the null object pattern is that your design is simpler if there are some invariant things that are true, that are always true about a certain object and all subclasses of that object. But there's something about the implementation or the requirements of your app that makes it hard to do that. So again, I'm going to use an example from my own experience from real life, which is sprinkled all over one of my applications is the idea that there's a bunch of properties you can ask about a customer. The problem is that in some places, those calls are made in a scenario where nobody has logged in yet. So if someone has logged in, then the customer object refers to a real instance of the class that supports all these methods, like logged in, last name, is a VIP. But if nobody is logged in, then there isn't any object on which you can call these methods. The naive way to fix that is any place that you would be about to call a method, you would first check whether @customer has a non-nil value, or whether it actually has a value that is an instance of the class. A way more elegant way to do it is to basically create something that is called a Singleton Class. And there's a technique in Ruby for doing this where you have a class that only has one instance of itself. And within that one instance, you basically selectively override the behaviors. You could also, by the way, do this with subclassing, where you can create a special class called the null customer class, which is a subclass of customer, but it overrides all of the basic methods on customer to do something harmless. So if you ask the null customer if they're logged in, it's always false. If you ask the null customer what is its last name, it's always anonymous, and so on. The idea is that you no longer have to worry whether it is A, legal to do these calls, because the thing you're doing them on is a fully fledged instance of a subclass of customer, and B, you don't have to worry that the calls return something unsafe. Right? So you know that, for example, last name will never, for example, return nil. It'll always return a string. Therefore, you don't have to do anything different or special if you're using it on the null customer. Null object is a great pattern for stuff like this. And in fact, one of the places I'm refactoring to use it is in this same email marketing list example that I started with before. Some of my customers do not use any external marketing service. So in that case, it would be nice, whoo, I almost fell off. It would be nice if they didn't have to worry about that fact. I can just create a special class called fake email list, which is it's a subclass of email list, just like all the other ones are. I can use true inheritance because I really do want to provide these exact method calls, but I will just override all of them. If you tell the email list to opt a customer in, it will silently do nothing. If you ask the customer to opt out, it will silently do nothing. If you ask it a question like, how many people are on your fake email list, it will always say 0. So it does something that is sensible. It behaves in all respects like a real email list, but it's effectively been stubbed out the hard way. So that's the null object pattern. And when I said one implementation of that involves using a Singleton class, a Singleton class is technically a class of which only one instance of that class is ever allowed to exist. So this is one way to implement the null object pattern, is that you create a Singleton class that, well, let me see if I have, yes, I do have an example. One way I can do this is within my regular old customer class, I can declare a class method that will do this little bit of Ruby incantation, which is I'm going to add to the set of all known classes a thing that is an instance of a customer. So again, don't worry too much about the syntax. I just want to give you the flavor of one way to do this in a language that supports it particularly elegantly. I'm essentially creating a brand new class, but the only contents of that class are this single instance of it. And now that I have that single instance of it, I'm just going to override all of the methods in my regular class, and I'm going to do them to do something that the null customer would do. The only refused bequest I'm going to have is this one, that if I try to assign a new name, in my example, I'm raising an error. I could also have just sort of silently done nothing. But again, the idea is that this is some languages actually have a specific mechanism for doing Singleton classes. This is sort of an elegant way to do it in Ruby. Do not worry too much if the syntax looks a little bit weird. But what is the concept of a Singleton class? There's one instance of it ever. And in that instance, one of the things you can do with that instance is you can use it to implement the null object pattern. The other related one, and I believe this is one that somebody brought up, is the idea of a proxy object. And the concept of a proxy is that it behaves the same way. It implements the same methods as some real object, but for some specific reason, it does something different than the real object would do. So I suppose you could argue that the null object pattern is actually a specialized case of the proxy, where what the proxy object is doing is sort of nothing. But in practice, proxy objects are usually used for more sophisticated things. So for example, you can imagine a proxy object, one of the ones that you've already seen, is when you do these collection associations. If a movie has many reviews and you say movie.reviews, it may not have occurred to you to ask the question, what kind of a thing is returned by movie.reviews? And what we've been saying is only half true. We've been saying that it returns an enumerable collection. But that's actually not what it returns. What it really returns is an object that if you ever ask it to enumerate itself, it can do so. And in fact, it won't do so until the moment you ask. So the actual database query associated with this doesn't happen until you try to start pulling out results. However, for all practical purposes, this behaves like an enumerable collection. You can ask it to enumerate itself. You can dereference a specific element. So it is a proxy object in that it behaves just like the thing that it looks like, an enumerable collection. But the way those behaviors are implemented is dramatically different from if it were a real enumerable collection. Another example of this is if you have an application, for example, that deals with things like email sending. Normally, the thing to which you would send an outgoing email is some object that is intended to model an email server. But if you're disconnected from the internet, one thing you could do is have a proxy object that has the same behavior, so it can accept a message for delivery, with the understanding that the actual delivery won't occur until much later when the app gets reconnected to the internet. But from the point of view of whoever calls it, it's the same idea, right? It's an object that, just like a real server, it has a method that means send this email. You can do the same thing with printers, right? You can have if you think of the save as PDF option when you're printing something, That is an example of a proxy object that does all the things a printer does, but the way it implements them is it saves them to a PDF file instead of actually sending the content to a printer to be printed. So that's the basic idea of the proxy pattern, and I don't know if that does or doesn't address the use case that you were talking about. Yeah?
What is the point of the null object pattern? So
When would you use the null object pattern? Typically, so the most common case is there's a kind of object that is used all over the place in your app, but there are some cases where the object in question, the instance that you have, doesn't correspond to a real instance. So the example I gave was most of the time there's a user logged into the app, and the object that captures the concept of a user can just be that user. So anything that is safe to do to a user, you could do to that object. But what do you do if you've got code in your app that might be executed when someone's logged in, or it might be executed when nobody is logged in? You could have two versions of that code, but that's sloppy. You could have one version of that code that checks if somebody's logged in and then does two different things. Or you could always have someone be logged in, but when there's nobody really logged in, the logged in person is this user that has these fixed properties, and it's always just safe to pass them around. So that's the most common scenario, is there are some situations in the app where the object might not look like a normal version of that object, and you don't want to have special case checks just to check that condition in every such place. That's the classic null object usage. Yeah?
Is the work being deferred in this example, or can you explain how?
So can I give an example of work being deferred? So in the movie.reviews case, work is being deferred.
Yeah,
But-
is it possible to explain how it's working?
In this example? Well, in this example, it's not clear that work is being deferred because the idea of deferment would probably happen inside of do something. Right, so I mean, deferring just means, it doesn't have anything to do with class design. It just means pretend to agree to do something now that in fact won't happen until later. So a more realistic example of defer would be like printing, right? Actually, when you print, it's not the case that you are talking to the actual guts of the printer. You're talking to an object that is basically pretending to be a printer and saying, OK, I've printed it. But as you know, what that really means is I have queued it, and it'll be printed soon enough. Unless the printer crashes in between, and then the proxy object is no longer a perfect proxy. So I'm just using deferred work as an example of a use case where a proxy object might be useful. If you can't talk to the printer, you can provide a stand-in that claims to have talked to the printer, but it won't actually do it till later. Right? But there's nothing about the class diagram here that specifically implies doing deferred work. The class diagram is just meant to say that the service proxy thing, as opposed to the real service thing, have exactly the same interface. They can be safely substituted one for the other for the actual service. That's all the diagram is meant to say. A couple more of these. And by the way, I recognize that it's a little daunting to try to have to be told about all these different design patterns. And now I'm like, OK, be on the lookout for when you can use the proxy pattern, and you better use it. Nobody learns to use design patterns that way. And that's the reason that whenever possible, we've tried to present it as, here's a real use case that if you didn't use the pattern, your code would be messy. And sometimes you're going to find that you just finished writing code, and now you look at it and you're like, that looks kind of ugly. And it's not clear why it doesn't smell right, but it doesn't. That is how you learn to use design patterns. It's by writing code that is initially kind of bad, and then afterward coming to the realization that, oh, if I had thought about doing it this way, I could have done it better. And that's fine, because the next time you do that type of code, it'll come to you, and you're like, OK, I'll just solve this using the proxy pattern, and you'll be golden. So don't feel bad if this feels like, how am I ever going to know when to use these? Everybody goes through the same things. That said, a couple of other useful patterns to know. The idea of the composite pattern is when you have a certain type of model where operations on a collection often make sense as the same corresponding operations on a member of the collection, or on the aggregate, if you want to call it, instead of a collection. So again, I'll give an example inspired by, although not currently implemented. Well, it's sort of implemented by an app that I maintain. I have different kinds of tickets that I distinguish. For a simplified version of the argument, we'll call them regular tickets, VIP tickets, and subscriptions. And all three things have in common that you can buy them. So they have a price. And because you can buy them, they are a thing that can be added like to a shopping cart. However, Regular and VIP tickets are for a particular kind of show, or usually for a particular date. A subscription is actually a placeholder for like 5 other things. So when you buy a subscription, what you actually are getting is 1 ticket to each of 5 or however many other shows. But a subscription still has a price, and it still can be added to an order. So essentially, the way that you model something like this is there's whatever the base component is, the behaviors that don't change go here. So you might even think of this as an interface in some cases. So the base class is what are the things that are the same whether you're doing it to an individual item or to an aggregate of those items, right? So that it has a price, that it can add itself to an order, those things are in common. Then you have the individual object, and it may be that the collection consists of multiple instances of these. There may be some operations on the individual objects that do not make sense on the component. So there may be additional methods here that are not methods up here. By the way, why is that not a problem with Liskov substitution? If I'm saying that, that these subclasses, right, and I'm using the open arrow, so I really mean inheritance here, why is it not a Liskov problem if I have additional methods here that do not appear in the superclass? You can take my word for it, by the way, that it really is not a problem. Yeah?
Because the problem with Liskov substitution is when you have methods in the superclass.
Right, exactly right. So if I had methods in the superclass that the subclasses couldn't handle, that's the problem with Liskov substitution, right? Liskov just says anywhere that this component is legal to pass, then either of these subclasses should also be legal. And that's fine, because if it thinks it's getting a component, it's not going to occur to the caller to try to do these specialized operations because they aren't part of component. So there's no Liskov problem in subclasses that extend the behavior of the superclass. That is totally cool. So we have the individual object, which may have some behaviors that don't make sense for the component, or that are not common to both. And then you have the collection, which is also called the composite, and it has methods that only make sense on the collection. So for example, asking the composite item how many of something it has makes sense at this level, but it does not make sense up here because the superclass is supposed to be capturing only the common ones. In code, here's a way that it might look. I could have a base class of ticket that has things like price and add to order. That's what the behaviors are that whether it's an individual instance or an aggregate of them, either of those things make sense. Regular tickets have the idea of being part of or associated with a particular date. So that's something that would go only in the item model. Same thing with a VIP ticket. And then a subscription or multi-ticket or whatever we want to call it has other methods like which tickets are included in you, or add other tickets so that there are more tickets included in you. Those are things that don't make sense except on the collection. And that's kind of the key for the composite pattern, right? You're separating out things that make sense for both the individual item and the collection. And then you've got things that only make sense on individual items, things that maybe only make sense on collections. You can actually subclass both of them directly. You can see that there's a few differences, like and then when you implement some of these methods, for a multi-ticket, what does it mean to add a multi-ticket to your order? Well, in the multi-ticket class, we will override the common add to order method, and we'll basically call the superclass method on each individual instance. Right? So we still have an add to order method. It still has the same interface. Liskov substitutability is being preserved, but we're overriding the implementation of these methods because the behavior of price or the behavior of adding itself to an order is going to be different for the multi-ticket than it is for any instance. So it is still true inheritance, right? We're reusing some behaviors, we're overriding some behaviors, but it is always safe to provide one of these wherever that would have been called, because we can sanely implement all of the methods of the superclass, even if we have to override a couple of them. So that's a pretty standard example. If you end up using something like this, there is actually a mechanism called single table inheritance that lets you put all the subclasses of the model into the same table, which is pretty interesting because the discussion from the previous example suggests that the subclasses may have attributes that are not shared by the parent class, which means that depending on whether a particular row of that model table is an instance of the base class or one of the subclasses, which attributes are dereferenceable may actually make a difference. And that's why it's nice that Rails actually has some machinery that manages this for you. Basically, if you have if you add a column called type, that column is assumed to be the name of the subclass of the appropriate object, and Rails does all the right things. So if you happen to pull out something from the database whose type column was set to regular ticket, even if the base model, the ticket or the table is called the tickets table, when you pull out something whose type column is set to this, Ruby will cast it to the correct type. So what you will get back is an instance of either the base class or the correct subclass, depending on what the type column says. Okay, so it's use the mechanism with care, but it's a mechanism that is there specifically to help with design patterns like the composite pattern, which I think is pretty cool.
All right, no comments there. We'll go straight to the next video.
So here's the last of the solid principles. The Demeter Principle says, only talk to your friends, not your strangers. Or more precisely, an object can call methods on itself, which means methods that are part of its own class. If the object has components within it, right? So in our example before, where we redid the square example, where inside the square, one of its components was a rectangle. OK, well, that's cool. That implies that there's actually a certain level of intimacy between the square class and the rectangle class. So you can call methods that you know about on your own instance variables. But that's it. You can't call methods on the results returned by those things. And I'll show you, again, the gist is on GitHub, but I'll show you the actual code on the screen because it's easier to read. OK, so let me walk through this example and the problem that arises and how it gets solved. And the scenario here is that we have a customer and a paperboy. Those are the two classes. The customer has a wallet. We assume that here's a wallet class, and the wallet knows how much cash it has. But we haven't specified the details of how they're implemented. And here is a bad implementation of the paperboy class when it's time to collect the money. If the paperboy is trying to collect a certain amount from a certain customer, this is the problem. This is basically the line where the Demeter violation occurs. Right? So what's happening here? The paperboy must know something about the customer. Right? That's fair because they have interactions. And you can imagine that the paperboy even knows that the customer has an attribute called the wallet. But the paperboy also seems to know that the wallet has an attribute called cash, and that specifically that attribute can be reliably inspected to determine how much cash is remaining. So basically, the paperboy knows way too much about a class that is not its friend, about a class that is sort of 2 degrees of family removed or something like that, right? You can't help the paperboy knowing some things about the customer, but it's already iffy that the paperboy knows that the customer's wallet is an instance of a class that has this cache method. Like, that's a lot of knowledge seeping into the paperboy. So one way that you can tell if you're doing this is when it's really hard to write the test. And here is an example of the kind of test that you might write if you wanted to write a test for the collect money method. Notice that the collect money method is going to take a customer and an amount. And based on what we have seen about mocks and doubles, we're going to want to somehow control the return values for customer.wallet.cache. Because we want to test the case when the customer doesn't have enough money. We want to make sure it raises the right error. But look at what we'd have to do. First, we'd have to create a double for the wallet so that we can say customer.wallet legally. And on that double, we have to create a double for the customer. And on that double, we have to create another double for the wallet so that we can stub all the way down this chain. See what I'm saying, how that makes sense? So customer.wallet, or customer is a mock object. Customer.wallet is also a mock object. And it is just smart enough to return a value for cache. And now that you've set up all that stuff, now you can actually make the call. So some people call this a mock train wreck, because basically you have a string of A.B.C, and you need to stub out everything along that chain just to make your test work. That should be a signal that something about this method is going wrong, and that's the violation of the Demeter principle. By the way, some people have asked if there's like some Greek myth about Demeter, and that's where this comes from. No, there was a software project called Project Demeter, which I don't even remember what it was, but that project is credited with sort of coming up with this formulation. So It's the Demeter Principle. Sorry, it isn't something more fancy. So how do you fix it? Once again, we turn to our friend delegation. And I'm going to show two versions, but the second version is better. A version that is at least an improvement over what we did is straight ahead delegation. So notice that the wallet class is now gone. I mean, it still exists, but it's no longer part of our code flow because we've implemented a cache method within the actual customer. Now, true, the only thing that method does is delegate to the wallet. But now, at least, the knowledge that a customer's cache is controlled by the wallet, that knowledge is now encapsulated within customer. All mention of a wallet is now gone from Paperboy. So this is somewhat of an improvement because now the Paperboy just has to know, I can ask the customer if the customer has enough cache. How the customer determines whether they have enough cache is none of my business because I only talk to my friends, not to strangers. So if the implementation of how the customer manages their cache changes, then the code down in Paperboy is insulated from that change, right? And that's the whole goal here is try to avoid needless churn that results from changes like that. So that's an improvement, and all we have done is delegate, right? We have created a method within customer that the only thing it does is just forward the call to the method that actually does the work in wallet. We haven't changed any of the underlying code. A still better way to do it, though, is to delegate the entire behavior. Because here, in the example on the top, even though the way that the customer's cache is measured has now been sort of isolated a little bit from the concept of a wallet, there is still a fair amount of behavior being specified here. Because, for example, what if the customer has a best buddy from whom they can do an instant borrow, therefore they have enough cache, and now you need to somehow reflect that, like you need to manage the customer's cache to reflect that. That should be a perfectly legal way for the customer to pay the Paperboy, but there's nothing about this behavior that would allow you to implement it because you're basically making assumptions about what customer.cache means. So if you do a further round of delegation, it's like, instead of delegating the computation of cache, I will delegate the entire behavior of moving cache out, right? Which means now, excuse me, in the wallet class, we can put our logic about what to do if there is not enough cache. And here, later, we could decide to make the change of, oh, if there's not enough cache, we'll do a transfer from PayPal, and now there's enough cache, or whatever, right? The idea of withdrawing is now a behavior. So rather than just delegating a data attribute, delegate the behavior. In the customer class, the way that you pay is you ask your wallet to withdraw that amount. And again, if you wanted to change what paying means, for example, maybe there's a way to pay that is not solely based on the wallet, you could hide that behind this behavior called pay. And now, all you have to do is ask the Paperboy to tell the customer to pay whatever the amount is. So the reason that the bottom example, in some sense, is superior to the top one is you have hidden more things, right? You have basically said, I'm going to talk about what I want to have happen, pay, rather than how I want to have it happen, customer.cache, which is in turn an improvement over how that how happens. So it's not just that the customer has cache, it's that I know where the cache is, right? So if you see a lot of a.b.c in your code, check to see whether, and by the way, sometimes that's just because you're calling standard library methods, right? Like if you have a collection and then you're sorting it and then you're mapping something, that's not really a big deal. But if the a.b.c is that your class A ends up knowing non-trivial things about the implementation of class C, that's a problem, and it's almost certainly a Demeter violation. Just to quickly do a review of the 5 that we looked at, single responsibility, a class should basically only do one thing. One way that you can measure if it's doing one thing is you can look at a score like the lack of cohesion of metrics, which basically means are most of the instance methods touching most of the instance variables? If the answer is yes, then they're sort of tightly integrated. It's probably only doing one thing. But if you end up having cliques of methods that talk to cliques of variables and they're separable, then maybe there's really more than one class going on there. And this is a particular risk of running into when you write model view controller apps with a framework like Rails, because the tendency is once you've created a model that's based around a table, you start sort of dumping all of your behavior into the model. That's better than putting it in the controllers and views, to be sure, but when the model has other things that it needs to depend on that are not part of its one responsibility, those can go somewhere else. There's a directory called lib, L-I-B, which is part of every Rails app. That's a place where you can put other classes that are not directly tied to an active record database table, but provide functionality that's used in other places. So extracting a class is sort of the obvious way to do that. We talked about the open-closed principle, which says you should try to write your software in a way that adding or extending functionality should not require modifying existing code. And one classic symptom that we looked at is if you have code where there's a case statement based on many variations of how to do a task, and it is likely that in the future you would add more variations on how to do it. We looked at a couple of different ways to solve it, but one of them involves the abstract factory pattern, which means how you create something whose type isn't known until runtime. And then we looked at two different variations for capturing the idea of different ways to do the same thing. The template method, where you have an algorithm whose steps are basically the same, but the implementation of steps could be different. We also looked at the strategy pattern, which is the overall task is the same, and the high-level interface to doing the task may be the same, but the steps are not necessarily the same, so you have a lot more generality in how it's implemented. And we also extended our example with this idea of the decorator design pattern, which is you have a base class and you want to have sort of stackable behaviors where each decorator includes as one of its components either the base class or another decorator. So they all have the same type signature, and then you can sort of stack the behaviors that you want. So that was the PDF example that we did. So again, notice the sort of approach that we're trying to follow, which is we're tying each of the principles in solid to the kinds of things that can go wrong that illustrate you might have violated the principle, and which patterns from the design patterns literature could be used to try to remedy it. L was for Liskov substitution. Basically, it's trying to capture one of the most common misuses of inheritance, where the behaviors you're trying to capture are not really truly superclass-subclass relationships, where even if the subclass wants to reuse some of the work of the superclass, which is a perfectly legitimate thing to want to do, the subclass isn't really a specialized version of the superclass. In fact, there are things the superclass can do that make no sense for the subclass. That's the canonical Liskov violation. And like a number of other examples that we saw, the idea is you should question whether inheritance was the right mechanism to begin with, when in fact one of your choices is composition, where one of the elements of your class is an instance of another class to which you can delegate the behaviors you wanted to reuse. Right? So the overriding goal of reusing behaviors, good goal, but a lot of the time inheritance is not necessarily the best way to do it, and that's what Liskov substitution tries to capture, and the idea of composition with delegation will help you avoid violating. I is for injecting dependencies. So here the problem is you've got one component that depends on the functionality of a second one, and even if that functionality may stay the same, the interface to the functionality may change. So the idea is you essentially create an intermediate interface that from the point of view of the caller is exactly just what the caller needs. You find ways to adapt that to the callee. So now both the caller and the original callee in some sense have to satisfy the contract of that intermediate interface. And it's called dependency injection because they both are now dependent on being able to satisfy the intermediate interface, and you have injected it between the two original pieces. So like a number of other approaches, this creates more code, but by providing that layer of insulation, it actually makes the code potentially easier to change. And if you remember the example that we walked through, we had the idea that when two classes sort of have too much information about each other, not only are you going to have an interface that separates the two classes, but you can also delegate entire behaviors through that interface. And then finally, the D was for the, whoops, sorry, hold on. Sorry, that's the wrong refactoring thing for injection of dependencies, but I'll have to fix that after lecture. That was actually the example that we used for Demeter, which is the problem that arises when you've got a chain of calls in which the first class knows way too much about the last class. And that's the typical problem that is manifested by having tests where you find yourself having to do a long chain of doubles just to get to the point where you can run the test. That was the example where we saw that one way to fix it is to delegate entire behaviors up to the other class so that you're no longer exposing the innards of the class to one that is more than sort of 1 degree removed away from it. So sorry about the slip up on the previous ones. we've actually seen in the Rails framework itself, there's a number of patterns that you've sort of been using without realizing it. We walked through an example of how the idea of the different databases that Rails can work with is an example of the adapter pattern, because from the point of view of active record, there's a single interface that provides generic database functionality, but the different databases that could be under that interface have very different APIs themselves. So that was sort of a canonical example of using the adapter pattern. The abstract factory pattern is used there too, because at some point when your app starts to run, you will have to create a connection to the database, and until runtime, when that database.yml file is read in, Rails doesn't know which kind of adapter is going to be required. So the code has to be prepared to figure that out in real time and create an instance of the right subclass. When we talk about caching, which is in part 2 of the DevOps lectures, we're going to see that one way that you can do caching is what's called the observer pattern, where you want one class to be notified when an interesting event happens in another. The proxy pattern we mentioned is already used in things like associations, that when you dereference a has-many association, what you actually get is an object that can be made to behave, for example, like an enumerable, but the way it's implemented, it doesn't actually do any of the work until you try to start pulling results out. So it's an object that has the same interface as what you would normally model, right? In this case, a collection, but it's not actually implemented that way. The Singleton pattern, ensuring that there's exactly one of something, creating a class that only has one instance. As it turns out, there's something called Inflector, which is the Rails class that knows things like the plural of person is people, so that if you name your tables according to conventions, the right things will happen. Inflector is a class, and there's only one instance of it, and that instance has a lifetime that spans the runtime of your entire app. The Decorator Pattern, if you look in the book, there's examples of using what are called scopes, which are basically ways that you can capture sets of conditions like wheres or orders for your active record queries, and those conditions can be stacked together. So the examples that we used in lecture included things like movies.forKids, and for kids is defined as a scope that just checks the rating column to see if it has a certain set of values. And those things can be stacked on top of each other. So that's actually an example of the decorator pattern at work. You can define your own scopes, and each scope decorates the behavior of the base active record model that you're putting the scope around. So if your model is the movie model, then in some sense, anywhere that you could use movie.something, you could use movie.forKids.that same thing, right? It is decorating the behavior of a base class and providing some specialization on top of it, and it's composable with other decorators. We haven't talked in detail about the command pattern. There's a lot more patterns that are discussed in the textbook that we won't have time to do in lecture. But when you write a migration is basically saying, run this command to make a change to the database. And one reason to use the command pattern is if a command has a well-known undo. So in a migration, when you create a table, how would you undo that? Well, you destroy the table. If you have a migration that adds a column to a table, what does it mean to undo that? Well, it means you take that column out. So the command pattern is typically used in scenarios where potentially the ability to undo something would be valuable, and therefore the things that you can do are sort of structured as, here's a list of commands that you can try, and each one has a well-known inverse. And finally, the iterator pattern, which is having a collection be able to traverse itself, a collection that knows how to enumerate its own elements. Because of the way collections work in Ruby, you may have seen this by now, the iterator pattern is actually used everywhere. So when you have a collection like an array or any kind of enumerable, and you use each, and then you provide a function that does something on each member of that collection, you are using the iterator pattern because the implementation of how to get each of those elements is being hidden from you. All you know is that if you call each on the collection, one at a time you'll get the elements back. But it tells you nothing about how those elements were stored. It may or may not tell you something about which order you get them back in, unless the collection specifically says that it is an ordered collection. So the idea that when you have a collection of elements, it knows how to traverse itself and how to yield each element in order, that is the essence of the iterator pattern. And in Ruby, because that's how iteration is basically always done, you're sort of always using it without realizing it. So all of which is to say that the reason design patterns exist is that they actually are useful in solving real problems. And as you write more and more code and you start running into situations where the code feels viscous, where it feels harder to make straightforward changes than it should be, that's when you sort of turn back to the refactoring book and you say, OK, what is it that I'm running into here? And are there design patterns that can help? And I wish that there was a way to just sort of teach design patterns, but the only way to teach them is to kind of run into them and stub your toe and then realize after the fact, now I understand. The problem is this is crying out to be, I should have used observer to implement this. It would have been much cleaner. And then you go refactor. So I think another reason that Agile has gotten as much traction as it has is that the idea of dealing with change on all timescales, it also acknowledges that as programmers, we're human. We are not always going to have perfect clarity at the moment we're starting to design the software and say, I know exactly the right set of design patterns that's going to make all of these modules work. Sometimes you won't foresee what the right answer is. And having the facility to say refactoring is something that's an ongoing process. And this is just one more example of refactoring. It's recognizing that you just missed an opportunity to do something a little more elegantly, but it's OK because you're armed with the intellectual tools to go back and fix it. So good times. Most of the solid stuff actually came out originally from statically typed languages. And there are some principles that have more impact there, because in a statically typed language, when you modify the type signature of something, potentially you sort of have a ripple effect on all the things that it depends on. So if there's some file that's part of a library and a bunch of other projects depend on that library, a change to that file that modifies type signatures implies that the library has to be re-released. Everybody who is depending on it has to relink to the new library version. So things that require recompiling or change the type signature, those are not problems that arise in Ruby. But nonetheless, I still think the solid principles are useful, because the emphasis is how can you make your code reasonably elegant, but also accommodating of a certain amount of change at those extension points. And just because you don't have to relink the library every time you change it, doesn't mean that you should not be worried about that, because whoever maintains your code going forward is going to have to think about it. So kind of my summary of design patterns, they exist because over and over again, the same class of problem got solved. And somebody figured out, there's actually some commonality in all of the solutions that worked. And you try to encapsulate that with things like class diagrams and explanations. They're not things that you can sort of apply mechanically, right? You have to sort of have some thinking to figure out how, for example, the delegation and composition applies to your particular software problem. But the basic idea is that you're not just reusing code, you're reusing structure. You're reusing ideas about structure. A few of the patterns that come up are what we say reified. In other words, they're first-class abstractions in Rails because they're really useful in some specific way to SAS. For example, when we talk about caching, caching is a fundamentally important performance operation you have to do for high-volume software as a service. As it turns out, the observer pattern is a really good way to implement caching in a database-backed application. Therefore, there is a first-class abstraction for the observer pattern in Rails, and it's designed for doing things just like that. So overall, it's separating what changes from what stays the same. The most we can do in a one-semester course is sort of give you an introduction to it so that you know this is out there. That before you start solving a problem, understand what the problem structure is, and take a step back to see whether this sort of smells like something you've seen before.
All right, so that's the main content for design patterns. So we have one more video left for that looks at the design pattern from the waterfall perspective. Before we get to that video, I also want to give a quick recap. So I think we've talked about a lot about the solid principle and all that. Honestly, probably you won't be able to remember that just by watching that once. Even watch it 3 times, you may not be able to understand and remember that until you, like the professor said, until you run into the actual problem and then using one of those to solve it, then you will remember and fully understand that. But yeah, just I think the point for this module is really just let everybody know that there's something out there called design pattern that that has been proven to improve the code quality. But practically, I would say what you really could do is just read a lot of code, and then ideally read good and beautiful code. What you could do is like pick a popular framework, a popular library for Ruby, then a popular gem, and some may be too complicated. For example, if you want to read the code base for Rails itself, it might be pretty challenging. What you could do is, take one a part of Rails, like Rails is actually composed of the router, the controller, the view, active model, that kind of thing. You can take part of that and try to read it. I actually did that when I first started. At the beginning, it was hard to read, but as I spend more time, it gets easier to read. And then also, especially when you read a lot of good code, beautiful code, you kind of naturally develop the instinct, the taste. And then once you're used to those good, beautiful code, and then as soon as you see some smelly code, you may not have the theory clearly say what's wrong with that, but at least you will have the feeling that, hey, this code, there's something wrong with this code. So I do want to encourage everybody taking a course throughout your career, when you get a chance. Like I said before, when you get a chance, learn something new, especially the popular ones. Every once in a while, the technology just evolves so quickly that there's always some new thing comes up, new tools, better tools that's developed. So it's always good to, stay on track. But then also the other part would be, develop your instinct, or what I heard from designers, their teacher would tell them to just spend time looking at beautiful things, beautiful designs, and then naturally will develop the eye for the beauty. Same idea here. Just spend time reading codes, especially good codes. Sometimes you may not be able to tell whether the code is good or bad. So, but at least by choosing a popular one, you would have a good chance to read mostly good code. And then, over the time, you will develop the taste for good and beautiful code. And then once you run into bad code, you will tell there's something wrong, and then you could start to think, oh, is some of the design pattern can be applicable to fix this code smell, that kind of thing. Read a lot and try to write it out if you gets the project an opportunity. And then, other than that, the only key takeaway I would say is remember composition over inheritance, as we've repeated a few times. When it makes sense, try to use composition instead of inheritance. And the other thing I would say, that would be single responsibility principle. Just for every single class, try to let the class focus on one thing instead of doing multiple things in itself. Sometimes it's actually okay as long as the project is not too complicated. But I would say if only that's the other takeaway, remember that. And then practically what I usually do, and I think many people usually do, is just one class per file. Just don't put multiple classes in one file. And then second, just make sure no file gets too big. Meaning like if like an active model, a user model, for example, gets too complicated, then that file will be like going more than, let's say, 500 lines of code. Then at that point you will know, okay, this file is too big. There must be something wrong. Since we're just limiting one class per file, so by looking at the file size, we can sort of tell if there's too many stuff going on within one class. And then when it exceeds a certain limit, then it's time for you to do some refactoring. But otherwise, usually it's not too bad, I would say. Especially for a project that's not too complicated. And I have a couple of design pattern books, but since we're teaching this course using Ruby on Rails, so I guess I'll just share that book later in the chat room. And I think it's a good read. It gives basically a lot more examples, I would say, compared to what we've watched in these videos. And then because video is especially for people joining live stream, you probably won't be able to just pause and then actually look at the code. But to understand design pattern, I think really you will need to take the time actually to go through the code, understand what that code is doing, understand why it's bad, and then read the refactored code and understand why it's good. So it's gonna take time to read the book and then to actually see those examples and understand that. So I'll share the book later in the chat. It focuses on Ruby, but also there are other books that's more general, but usually design pattern books are specific for each programming language. Like for me, I first read a couple of chapters from the Gan of 4. You can probably find a copy of Gan of 4 online. Just Google it. You should be able to find it somewhere. And then I think I read a book that talks about that. Okay. Sorry, I got a phone call. So what I'm talking about? Oh yeah. So another book for Java, and design pattern I think was first taught, really first introduced in the Java community because it's more important, honestly, for statically typed language rather than a scripting language like Ruby. So yeah. Anyways, you can probably also find books there. But yeah. Okay. Anyway, enough for the design pattern book. I'll share the book later in the chat room. Okay, so that's enough comments for the recap, and we will watch the last video that looks at that from the waterfall perspective.
So what the Pattern documents also that's what we called it in the early editions of books, big design up front, right? So they are purposely taking the time to do the design before they do anything. So it can result in a good software architecture. In particular, if you remember from the Plan and Document approach, you write this elaborate and long specification called the SRS, and then you take that and you break it into problems, and then for each task you try and find the design patterns that match that. So in the waterfall or these other models, you start off with the spec and then you start before you write code, you come up with a pattern. So it's kind of like we talk, our test-driven approach to testing, you write the test before the code. Here they come up with the patterns and architecture before you do it. And then you get feedback from outsiders to ask about your design. That's a design review versus a code review. Do we have a good design? Are we using the right design patterns, the right software architecture? So a lot of the P&D approach is around trying to get good design up front. And so the Agile approach gets criticized, but you just start doing code without any design, and that you have to rely on refactoring to get the good the design patterns in there. On the other hand, you know, when they went to the mountain and came down with the Agile Manifesto, they had a comeback. They said, well, but when you do all that elaborate design up front, that's great until you start coding, because you're not sure this is really going to work, that it's even going to match the customer's needs, and particularly over time as the software evolves, you're probably going to have to change the design pattern, so you're going to have to do the refactoring anyway. So that's the comeback here, right? So kind of the question is, how much should you do up front? So you need to be able to plan for the storage for the app before you get started. You know you're going to be able to do databases. You should be thinking about horizontal scaling, which Armando will talk about soon when we talk about optimizations. And then the basic idea is just kind of common sense. If you've already done a project like this and you figured out what designs would work, or you learned from that and which design you wish you had, go ahead and start with that in the design. Factor that into what you're going on. Now, how do you get started in design patterns? This is the Gang of Four book. Goes out of its way to say that design frameworks are different than patterns. The patterns are these more abstract, narrow in focus, not targeted at the programming domain. They're trying to, when they're trying to popularize what a design pattern is, people are confused about it. However, if you don't have a lot of experience with design patterns, frameworks are a great way to get started. There's design patterns, you can look at the code to see what it looks like. I would say, kind of reflecting on this, that, I mean, when we got advice from industry about learning about Agile and planning to document, the thing that they wanted to say is very likely over your careers there will be new methodologies will be invented. I would say one of the weaknesses of Agile, it's got a lot of things going for it, but it really doesn't factor in design. So maybe there's going to be some new methodology that you'll invent or you'll see that'll get the positives of Agile, but bring in the importance of good design patterns and good software architectures, which is right now you have to kind of retrofit in.
So here we can actually see one of the solid arguments or a reasonable critique against Agile is that if we follow the Agile practice, then we're actually not doing enough design up front, which the end result is sometimes we're just building stuff without a good foundation. Or the underlying structure of how the code should be mapped out. And then I think it's actually a reasonable argument and largely correct. Versus like, where if the requirements is figured out first and then design follows, usually we end up with a much more solid solution in the code base rather than just going Agile, building components one by one, like step by step. Usually it's a bit more messy. So that's why there's still some goodness or benefit from the waterflow methodology. And especially for a project that's reasonably smaller, less complicated, it might be a better idea to go waterfall to figure out all the specifications and requirements and design everything up front. But that's about the design and the design pattern for the waterfall perspective. All right, so we said today we will end a bit early because we're pretty much on track with our content. So I'll just close here, just repeat on the homework. So for this week, if you go with the basic option, write a summary of the last chapter, which we'll actually talk about design, DevOps on Thursday. Otherwise, if you go with the bonus option, you can just continue to do what you have been doing for the past week. Let me see. Yeah, I should have talked about everything I want to talk. So yeah, so with that, we will conclude today's lecture, and I'll see you on Thursday. And oh, by the way, remember, since we're in the last 3 weeks, so if you have not yet, I would advise you to already get started with your final work, whether it be the essay or the final project. So yeah, just remember, the time is short. There's only 3 weeks left, so keep that in mind. All right, so that will be it for today. I'll see you on Thursday. Bye.